Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering Module 8 from the universe to the atom. Inquiry question 4, properties of the nucleus, and we're going to be covering the following dot points today. Specific focus is looking into nuclear fission reaction and also how does nuclear fission generate all that energy. Specific textbook reference points are these ones here. We are going to be comparing the concept of controlled and uncontrolled nuclear fission. We're going to also analyze quantitatively the mass energy equivalence in nuclear fission reactions. So, what is nuclear fission, and also how can we control how it reacts? Quite different from nuclear fusion. Fission is the breaking apart of an atomic nuclei. If you recall, the atomic nuclei is the constituent of the protons and neutrons, and we're saying that nuclear fission is the breaking apart of that nuclei there. What we can actually work out in terms of the amount of energy that's produced, we actually said that nuclear fusion produces much more energy than nuclear fission in the context of energy per a unit or per a kilogram of that radioisotope formed or broken apart. Okay, so the concept of nuclear fission occurs when you have a really large unstable nuclei that breaks into smaller fragments. Generally, to get nuclear fission to occur, we need a slow-moving neutron that needs to bombard the nuclei. That nuclei will absorb the neutron and split it apart, causing the sort of production of new radioisotopes, energy in the form of gamma rays, and 3 fast-moving neutrons. In some other contexts they have 2, but that's usually the process of nuclear fission. In this process, when we get the breaking apart of the atomic nuclei, we'll have a thing called the mass defect. Essentially, if we measure the mass before and after, there is going to be a slight difference in mass. Now, the reason why that's the case, as we talked about previously, that mass is being converted into energy. And that was originally stated by Einstein's famous equation, E equals mc squared. So mass defect occurs when there's a loss in the atom's mass, more specifically the nuclei of the atom, compared with the individual protons and neutrons or the other successive smaller fragments. The reason being is because that binding energy has been taken apart, which is the energy to separate the neutrons into its components. It is also the energy released in nuclear fusion or fission reaction. And the reason why we can say energy and mass are equivalent to each other is thanks to Einstein's famous formula. The other thing you should notice is the greater the binding energy, the harder it is to pull apart the nucleus. So for the smaller nucleus, it has a stronger binding energy, whilst the bigger nucleus actually has a lower binding energy. Okay, so if we kind of make a quick measurement in terms of the binding energy of the atoms, we'll find that the total binding energy inside any specific atom is going to increase with a greater number of protons and neutrons. That's the idea. However, we actually can work out that the highest binding energy inside a specific nucleus, it reaches a peak at iron, so element 26, and then it actually begins to plateau down to the more heavier atoms. That's kind of why we are saying that iron is quite a stable atom. Rarely will it undergo any nuclear kind of reactions. So anything before iron is going to experience nuclear fusion. Anything after iron is going to experience nuclear fission. Just because if you want to create nuclear fusion after iron, you have to actually put energy into the system to cause that to occur. We talked about some formulas to calculate mass defect. So we said that the mass defect is the final minus the initial. You can do it in absolute values because you are expecting that mass is a scalar quantity, so it should only have a positive value. We also stated that the binding energy is mass times c squared, so that's given by Einstein's equation there. Okay, so I might just write that down. So mass is always positive because it's a scalar quantity. When we're using this particular formula here, this will give us the value in joules, but in order to get that, we need to make sure that the mass is in kilograms. In the context where we are getting the mass in atomic mass units, then we times by the value of 931.5. This is just the similar value for c squared, but in the context of electron volts and given in mega electron volts. If you want to convert from mega electron volts into joules, then you must make sure in that process you times the charge of the electron, which is given here, charge of the electron on your formula sheet, times by the mega component. And so 1 mega electron volt is 1.6 10 to the minus 13 joules. Okay, so that kind of gives us a little context of where the energy comes from in a nuclear fission reaction, and counting for the laws of conservation of energy and all that. Next we need to talk about is what is controlled and uncontrolled nuclear fission. Okay, now firstly we need to talk about is why specifically we're using neutrons in this. Neutrons carry more energy and momentum at a slower speed because it's more massive than an electron. It has no charge, so it doesn't interact with any electron cloud, so it can be easily absorbed by the nucleus. And obviously, if you recall, the neutron, the ratio between the neutron and the proton, that's the thing that causes the instability in the nucleus of any isotope. The other thing with a slow-moving neutron is because it has low kinetic energy, it allows for the nucleus to absorb it better and to cause instability. Generally speaking, if we have a neutron-induced fission reaction, we can get 3 neutrons afterwards, which we can then use to cause more fission reactions. So if we look at this diagram here, imagine a neutron is going into our atom here. The fact that it's really small, it allows it to be absorbed by the nucleus. And what that absorption does, any excess energy in that absorption will cause the nucleus to oscillate. So it causes it to sort of vibrate in all directions. Or sometimes we can even call it resonates. So continue backward forward vibrations. And in that process, we can actually cause a little weak point in the center, or the neck point, that's holding the strong where the strong nuclear force is trying to hold the nucleus together. Remember, as the neck narrows, the electrostatic force begins to overpower the strong nuclear force. Remember, the strong nuclear force is only strong in really short ranges. So as we get further and further apart, our electrostatic force, so our electrostatic force will become more powerful than the strong nuclear force. In this scenario here, our strong nuclear force is way more strong or way more powerful than our electrostatic force. As soon as that happens, the protons will repel the other components away, and then we get the broken parts of that nuclei, which is the fragments of the nuclear fission reaction. There are two types of nuclear fission reactions. We have a controlled nuclear reaction. What that means is you only allow one electron, only allow one neutron, to react. So instead of the 3 that does get released in nuclear fission reaction, we only allow 1. So that means what we mean by controlled chain reaction, it's only one following the other. So one follows the other. When we talk about uncontrolled, what you can actually interpret from this diagram here is essentially instead of just allowing one neutron to collide with another atomic nuclei, we allow all 3 to collide. So if we have all 3 colliding, you can imagine the overall quantity of nuclei experiencing instability and then decaying will be a lot higher and then occurs a lot faster. We can imagine a simulation of that. So you imagine a couple of golf balls in a mousetrap. So this is an example of a uncontrolled nuclear reaction. Just one then makes contact with others and it all spreads apart. So the better you can at preventing these neutrons from colliding with other nuclei, then that will ensure it doesn't go out of control. The second part that influences whether or not something becomes uncontrolled is the mass of the nuclear fission. So the smallest amount of mass of fuel to sustain a chain reaction is called the critical mass. Okay? If the fission material has subcritical mass, then a chain reaction cannot be maintained. Okay, so once the neutron collides with one particular nucleus, then it won't one particular nucleus, it might not be able to release other neutrons to collide with other nucleus. We'll show some examples. If the fusion material is supercritical, so we have well above what is the expected amount to maintain a chain reaction, this reaction will become uncontrollable. So that's actually how they use the atomic bomb to make the uncontrolled materials with supercritical mass. So what I'm going to show you with this little simulation here, and I'll try and put this simulator in the links below that you can test it out. If we do a nuclear chain reaction, if we go below subcritical mass, we won't get a continuous chain. Essentially, meaning by you won't see a continuous emission of radiation. Once it's collided with one, it might just stop and that's it. And then we'll look at the uncontrolled one where it spreads apart to all the different atoms until obviously it runs out completely. So let's look at a controlled fusion reaction and an uncontrolled fission reaction. In the first one we have here, we have gone for the subcritical mass. And for our example over here, we've gone well above our critical mass, so it's the supercritical mass, or just plainly above critical mass. Might have just invented a word there. So here we have our first emission. You can see our neutron coming in. It collides with one of the nuclei. You can see that there is not enough uranium 235 isotope to latch onto the free neutrons. So once this neutron collides, these 3 or 4 in this case go in all separate directions and it doesn't collide with anything else. So we've got a fission reaction, but it's not sustained. It's not a chain. Okay. Next we'll look at a chained uncontrolled. Okay, and we'll start with it coming here. You can see once it collides, more neutrons collide, and then essentially you can see here it's become uncontrollable. All the neutrons have basically collided with most of the atomic nuclei inside this little atomic bomb replica here that we have. So that's the difference between controlled and uncontrolled. So what I might ask you to also do is just copy this component down in terms of when comparing with controlled and uncontrolled. You do need to have a supercritical mass in order to get an uncontrolled nuclear fission reaction. Alright, so if we just quickly summarize everything we need here, we know that for controlled nuclear reaction you only need 1 neutron, and all the other neutrons have to be either absorbed or lost in that process. If we compare in terms of energy output for a controlled nuclear reaction, it's very steady, so it's steadily provided. The more for the uncontrolled nuclear reaction, we need more than 1 neutron. We need lots, usually 3. Splitting of the nucleus allowed to hit other nucleus to form further fission. The energy in this case is rapidly released, and also, like we said, in terms of the mass, to have controlled nuclear reaction, we want it at the critical mass. And if we want uncontrolled, we want to be well above. So the supercritical mass of the radioisotope. That's what we're looking for. Okay, so just really be familiar with this difference. One is about only using 1 neutron, the other is using multiple neutrons. The very first person who actually came up with the ability or came up with the idea of controlling a nuclear reaction came in 1942, as you would know. That was around World War II. This guy was called Enrico Fermi, and he was able to demonstrate the ability of creating a controlled nuclear fission reaction. And this was actually, this image here was the actual design he created. It was actually quite incredible. So he used a couple of graphite moderators, so that's the fuel source. He had these controlled rods made out of canadium. Essentially what that was supposed to do is absorb neutrons. So again, like we said, if we want to control the reaction, we want to reduce the amount of electrons in the reaction. And you know, he used uranium and uranium oxide to produce these slow moving neutrons. Within 28 minutes he generated 0.5 watts of power. Now if you know much about power, it's not a lot, but the important thing was he was able to show you can generate your own nuclear reaction, you can maintain it, and you can stop the reaction. So you had that control that no one actually knew of the time or was able to produce at the time. And so I guess what that leads us to is the most famous type of controlled nuclear fission, and that is nuclear power plants. Obviously you'd see in a lot of famous, cartoons like The Simpsons, the nuclear power plant, they will never actually show you how it actually works. Similar idea for coal power plants, wind power plants. The idea is to get a giant magnet to rotate and turn the magnets, use the concept of electromagnetism to produce energy. The idea is very simple. You have the decay of uranium from these fuel rods. These neutrons are in continuous reaction, colliding with other uranium nuclei, and it's actually the production of heat and gamma rays that actually heats up the water that's inside the fuel source. That or this here, so you have the exchange of heat here that will boil the water, causing it to become steam, and that steam is going to be the thing that rotates the turbine that generates the electricity, or turbine and the magnet. So that's the idea there. So exactly what we said here. These control rods are designed to absorb any excess amount of neutrons. So that is to maintain a consistent production of heat rather than it just spreading in all directions. When that particular form of, or when that heat gets into the water pipes, that's going to heat it up, boil it, and cause it to turn the turbine and produce electricity in the generators. As you would know, part of this design means that it needs a lot of water, and so warm water has to be released, constant flow of cooler water needs to come back. So you would expect that the water culture near a power plant or a nuclear power plant will be quite warm. So it's, in a way, it is still quite non-preferred for the environment as well. So that's the idea. So this is just a quick little summary of what we said just then. So the main thing that actually controls this experiment is the control rods, the moderators, to reduce the velocity of the neutrons and also to absorb some of the neutrons. We do in this case use a supercritical mass that just allows us to release a lot of energy in one go. So that's kind of the idea there, but we can control it by using moderators or control rods to absorb some of the neutrons. We also use radiation shields, that's just to reflect some of the neutrons and gamma rays back into the core, so it avoids harmful radiation being exposed to humans. But that's just kind of a little summary there of where we can use controlled nuclear reaction. Let's have a look at the concept of uncontrolled nuclear reaction. So the following figure shows the structure of Little Boy, the atomic bomb dropped on Hiroshima in World War II. So using this diagram, explain how it works. Now if you want to just maybe jot down some notes, feel free to just pause the video here because I'm going to go through the explanation. Alright, so let's have a look. Just before we go into the actual response, the actual structure of Little Boy is you have two parts of highly rich uranium-235, but both of these are below the critical mass. So first thing is by themselves they won't be able to generate a chain reaction. Okay. We have a explosive spark and we have a separating tube. So what's going to happen to detonate this bomb is the explosive charge will create an incredible amount of pressure in this little valve here. That's going to push this subcritical uranium towards this other side, and that's going to make it a supercritical mass. They're going to start forming their decays or nuclear fission reaction, and that's just going to go absolutely out of control. So that's how it worked. So if we have a look here, might do some annotations. So here below the critical mass, so at this point here, this point and this point here, a a chain reaction cannot be achieved. So a chain nuclear reaction cannot be achieved. That's the idea. Upon detonation, that increase in pressure, so pressure increase, we have a pressure increase, we have an increased amount of force that's going to combine the two masses together, so combines the 2 uranium-235. That means that when it is combined at this point here, we reach a supercritical mass, which means we can obtain a chain reaction, and obviously it being supercritical, we can have a uncontrolled chain because there's no way the neutrons will be absorbed in this particular process. So that's why the bomb was so deadly. That's why for weird reasons Not Little Boy was very dangerous, and obviously it caused a incredible amount of loss of lives, as you would know. The other part of releasing the atomic bomb, as we said before, it releases radiation, so it can cause radiation poisoning, but it also produces an incredible amount of heat. So you would expect that a lot of people were disintegrated for those kind of reasons. So it wasn't a great point in human history, we can say the very least. So the last bit I guess we need to talk about is just do some calculations to predict the energy being released due to the mass defect. So using Einstein's mass-energy equivalence relationship for nuclear fission, and obviously showing forth that we are following the law of conservation of energy. Okay, so the last one we have is just these questions here. You can see some of these nuclear equations. So we have predict sustained reaction. Use these calculations to work out these questions here. I'll show you what the answers are in the next slide, so you can pause it here if you want to have a go. I'm not going to go through this explanation because we have gone through it in other lessons. So I'll go through it now. So this is just a little explanation of what we have with the uranium there. So the best way we can sustain a chain reaction is having multiple neutrons, or by ensuring that we have a sufficient amount of mass. Those are the two main ways of doing it. Okay. Alright, so that basically concludes our explanation of chain reactions, controlled and uncontrolled. So hopefully you found this lesson useful. If there is anything you need to recap on, please by all means do that. I'm Mr. Wong. Thank you for joining into the classroom, and I'll see you next time when we talk about the final inquiry question of this very last module, which will be about particle accelerators and the elementary model. So until then, stay safe.